what we've got is a bunch for you guys to hold. And this is the heavy one. The old ones are made well. The 1960s ones are junk. And we had hundreds of the 1960s ones, and most of them don't even work. I've got them piled up in a closet upstairs now. And here's the big one that I can point to. This one is designed a little odd. The basic thing that makes a meter is the torque on a current loop. All right, so when you see the copper color down there, that's your current loop. Okay? And like I said, on the ones that you're looking at, those are going to be horizontal. That's just the usual layout. They did this one sideways. No big deal. Okay? Then notice kind of the off-color brass, right? That's above and below here and will be to the left and right on the meters that I gave you guys. Those are your permanent magnets. Right, so like one of these is a north pole, and the other down here is a south pole. Right, and you can kind of see the magnets go around. So you literally do have, and they're bolted together. So typically the way they do something like that is they either do that with the meter in the middle, or they'll do and then a nice strong bolt that holds it together. Okay, which gives you kind of a broader region that has the North Pole and a broader region that has the South Pole. All right, so when you're seeing that surrounding thing, that's what you're seeing. Okay. So over here we have the current loop, and right along with it, north and south poles of a magnet. Okay. And then you guys have better eyes than I do, hopefully. I'd be embarrassed if you don't. Okay. So on those, you can probably see somewhere along that central axis. Notice the current loop is wound around a little bobbin. And is that still a word? It used to be. And, that little silver cylinder that the thing is round around. Hooked to it, you probably can see a watch spring. Right? A little spiral spring. This toy now, that toy later. Okay.
I didn't even need to touch it. Just attracted it, please. I didn't even touch it. I accidentally hit it.
And that's the consequence, right? Anything you touch, man, he steals. All right. All right. Okay. What you'll see is a little watch spring that's attached to it. On this one, they didn't use a watch spring. If you come down here, you can see kind of a copper-colored spring just off the axis there, and a secondary spring that's right there. And what those two do, they establish the equilibrium position, right? So that if it moves away from that place where the needle is going straight up, there's a restoring torque. Right? So here's kind of the picture so far. All right, so I've got my little steel cylinder that can rotate about an axis that's right there. Right? And I have hopefully the green shows up. I have a watch spring, right, that has an equilibrium position when a needle is going straight up to the middle of something. Okay? So this guy, its job is to produce a torque, right? When rotated, restoring torque, when rotated from the center. then I've got, let's see, I never know which way to draw it the first time. So let's say a north and south pole there. So I've got a B field. That's going across like that. And then I have that coil that's just wrapped around the thing. Right? And so we'll say that the coil has a lead that comes in here and a lead that goes out like that. Okay. So far, right, you know, a non-current carrying wire is not a magnet, right? It's not charged and it's not moving. So right now it's just reading 0, right? So the question is, what happens when I start turning on a little bit of current? Okay, so let's imagine, let's imagine I send current in this way. Well, you know it's going to have a magnetic moment now. Mu is Ni times the cross-sectional area of the loop. Right? But it's also just going to be a little bar magnet. So that's always the easy way to understand things. Okay. So this guy now becomes an equivalent. So let's see, it's going around the back over there and then coming around the front. So this guy becomes a little bar magnet with the north and south pole. Okay, which way does it want to rotate? Whoops, yep, you're right. Let's see, I got it wrong then. Let's see, B field going this way, the north. Yeah, okay. So let's say this is the negative direction, okay? So it's seeing the current going that way, it wants to rotate that way, right? And so what happens is my needle moves over by an angle theta. Okay? And eventually it's going to stop, right, because of the spring. So if I look at the net torque, right, I'll have the torque from the B field plus the torque from the spring. This one will be mu cross B. All right, so that's going to be, mu is going to be N times the current times the cross-sectional area. All right, then I'll have the B field. And then notice, note the torque is mu cross B. The needle has moved by theta, so the angle between the B field and the magnetic moment, right, because the needle is pointing right along the mu, right, perpendicular to the loop, that's going to be 90 degrees minus theta. Okay. So here I'll have sine 90 degrees minus theta, and a torsional spring, or even those springs that are set off from the axis, they're going to produce a torque that goes like Hooke's law. And so some kappa theta. And it'll stop when the net torque is 0. That'll be the equilibrium. Okay. So kind of the neat thing is, even though it's not exactly a linear equation, right, you have to kind of expand things out a little bit. Notice you have a direct correspondence between the theta and the current. So at that point, all it's doing is, oh, let's standardize stuff. I didn't put a scale on. So that's the meter part of it, right? And literally in the 40s they made really good ones. They still work. The meter by itself is called a galvanometer. Right? And remember, if I put it in line with a small resistor, I can use it as an ammeter. Right? So again, they pick the resistance and they set the scale. Right? And to change the scale, all they do is change the resistance a little. So same thing with the voltmeter. Right? They're just going, if you're going to use it to measure voltage, they'll just going to pick a large resistor and you hook it up in parallel. Right? And again, the idea is you can change the scale by changing the resistance. So when I found 100K on the resistor on the 2-volt scale, right, that probably wasn't too bad, and probably if I had the equipment to go up to a 200-volt scale and still read stuff, I would have found a bigger resistor. Okay? So if you look at what August is looking at, right, notice on this side, you've got the different inputs for different scales. And you watch the wires, that's why I didn't snip those wires. And then you look, oh, there they are. And then you look, the wires go into different resistors for different scales. Right? And that makes a meter. Okay. First thing. Good example of torque on a current loop, right? It's mu cross V and why the mu is important. Second thing, it's just fundamental technology. Does it make sense? Any questions?
I think it makes sense.
Okay. Third thing, really fine workmanship, not necessarily mass produced in a factory. So digital ones don't use that. What they use is the Hall effect that you had the homework problem on. Right? They send that set current through a little thin strip and look at the voltage difference across it. Okay, so that's the first stage, right? And that's the necessary thing to go on for the next part. So over here we have just the galvanometer, and I actually tried some of the 1960s and 1970 ones. Like I said, we had hundreds of them. None of them worked that I tried. So this is a 1940s one, and it works like a charm. And they were really, I have not been to a school that didn't have these, right? Just exactly that same model. I think they made them the same way for years. So if there's any current that's flowing, it'll go through there and it'll tick the galvanometer one way or the other, right? So the idea is to do Faraday's experiment. Right? And again, notice just having a magnet around the thing doesn't do a thing. Right? So it's hard for you to see, but the needle ain't moving. Okay? All right. Notice I don't have, I have one of the old magnets, and I don't have like a really large thing. It's really hard to even see something here, right? But here I'm doing what is supposed to be done, right? I'm taking this is the North Pole? Doesn't say. Okay, assuming this is the North Pole, I'm taking a B field that's going like this, but spreading out. So when it's through here, not many lines go through the area. As I get closer, more of them do. And
It's moving.
And you can just barely see a little thing. As it moves in, it moves one way. As it comes out, it moves the other way. That's the size of the effect that Faraday would have seen. So, a better magnet you can tell it moves a little more. Right? Still not really big. Okay, so next step. This one is actually not bad, as much as it's just a toy. North and south. So if I do this, I don't change the flux, right? Nothing there. But if I do this, there we go. If I do that, then I have Oh, okay, and you can stop, well, no,
Well, Aaron's
actually,
not
Wade
here.
is
Yeah,
gone
Wade's
now.
gone, Aaron's
Okay.
gone.
I was gonna say Molly's here.
Can you still record that to me?
Of course, yeah.
Send it?
Yeah,
Yeah.
that's why she's doing it, because
Okay.
that one won't follow me around a room.
Okay, perfect.
But they did. I talked on Monday to the dean, my boss. Okay, and they're going to try and get a tracking camera, and one that's better quality than that, so that you actually get colors show up and stuff like that. Okay, but notice here, right, I'm seeing a little more deflection, but only when I'm going from having the field go outside to piercing the area inside. Right, it has to pierce through the area. And notice when it goes in, it reflects one way. When it comes out, it deflects the other way. I can make that better by a slightly better loop. I'm missing a connector. Anyone see an extra little thingy like that?
Oh, I swear there was one over there. Wasn't there, man?
Ah, thank you. So again, just for the sake of it, a few more loops of wire and a better conductor. Come on, get in there. And one goes in on one side, one on the other side. So again, you can notice the same thing when it goes in. I'm just getting a better signal now, right? Anything that I do to the outside doesn't affect the flux. When I move in, it deflects one way. When I move out, it deflects the other way. If I move slowly, I don't get much. If I move fast, I get more, right? Increasing the speed of the change. So same sort of thing here. Just out of curiosity, I don't even know if this is strong enough to do anything. A little bit. It's about as bad as that was with the other one. Okay, so with a stronger magnet, you can see the effect a little more. All right, so as I'm going in, let's do the Faraday's law. All right, North Pole. So the B field's going like this. As I come closer, what's the change in the flux?
Positive increase?
Always give me a direction.
Oh.
Right, the plus and minus are directions, but point to me.
Oh.
Right, I'm doing this. How is the flux changing? Okay. It is getting bigger, right? Because I'm having more lines of B fill going through. In which way? That way.
Sure, yeah.
Okay? So positive to your right.
Okay.
Okay? So to cancel off part of that change, to have more to the right, I want to produce some flux to the left. Okay? So the current's going to flow that way, right? So that I get some to the left. And so notice when I do that, okay, that's deflecting that way. It's saying that's the positive. Which I guess makes sense because you can see it comes out over here. So that current is going in over there, coming in, and then going out. Okay? And then notice when I bring it out, it goes the other way. All right, so again, let's go through that practice with Faraday's law. Right now I have flux going through it. As I pull it out, I'm going to have less. Okay? So you give the direction to the change. I start off with some going this way, I have less going that way. So you can say it however you want to, less going to the right or more going to the left. Okay? So if I have less going to the right, to cancel off part of that, I'd like to produce some going to the right. Right? So that means the current's now going to go this direction, right? Which was the opposite of what it was before. Right? So first you establish the direction of the flux, right? Positive or negative, or left or right. Right? And the direction in which it's changing. Increase to the left or increase up, right? However it's going to be. Then you ask which direction does the current flow to do the opposite, right? Produce some B field in the opposite direction of the change, right? Or something like that. Okay. So, so again, approaching North Pole goes one way, approaching South Pole goes the other way, right? Because it would have the opposite effect, the opposite direction of the flux. And I think that's about it. I just have this because, again, we got better coils over here and a few more of them. So here I got a bunch of them. Right, so if I switch it around to this guy, let's see, the wimpy magnet ought to do something. Is that in? There. All right, more coils, more flux. And so you see a bigger change, right? And even larger with a more powerful magnet. Okay, and here it's easy to see. If I do it slowly, I get some change. You can tell how steady my hands are. Right? And if I do it faster, more change. Right? So proportional to the rate of change. It's okay? How is the Lenz's law part of it? I want to do it a couple more times? Then let's do it one more time. Okay, so South Pole coming out. All right, so let's see. Right now, since it's a South Pole, I know that the lines are going into it. All right, so at the beginning, I have lots of lines going to your left. Okay, as I pull it out, the field lines start not going through. All right, so my change is going to be having less to the left. Okay, that's what I have to oppose, the direction of the change. All right, so having less to the left, I want to produce some more to the left. All right, so the current would flow this way to go through it. All right, so again, you would see one direction.
Yeah, it came on.
Ah, rats, okay.
That one. Yeah.
It's always a doubt for me whether I'm just not seeing things well anymore or whether it's actually not working. Okay, so one direction as I pull it out, opposite direction as I push it in, since it's the opposite change. Okay. So that's that one, right? And you can do labs with it. I mean, you can figure out the area of the loops and stuff like that. But I figured it's just more important to see the effect than do it. Plus, I don't know if I told you guys, but when I ordered the current stuff, they gave us a nice free upgrade. They gave us ammeters and voltmeters that were wireless, so you could walk around wherever you wanted to carry the thing. Unfortunately, we have the old generation of interfaces that aren't wireless. So all of the things that I could have been doing with circuits, with getting a readout on the screen, I can't do right now. So I have both ordered some of their old-fashioned probes, right? And I've also ordered some wireless add-ons so that those things will feed into the computer, but none of them have arrived. So, but on these things, I prefer doing a lab like this anyway, because I think it's more important to see the effect and talk your way through it. Okay, there we go. So next one. Over here. Right, and with this one we can do a few things. This is the one piece of equipment that he had that I was really happy he had. Okay, it's not the best. It was covered with dust, but it's like an exciting one. Okay. The one that I really like, it's like 6 feet tall. Okay, so notice, well, okay, a couple of things. First off, this is a soft iron core. Remember, what makes iron soft is the ability for the dipoles that are the individual atoms to all line themselves up. Right? So this has got that. This purpose is just to make the magnetic field stronger. And if you look at it, right, you'll notice that it's not solid iron. Right, it's little rods that are separated by an insulator. Okay? That doesn't affect the alignment of the dipoles. Right, but we'll talk in a little bit about why it's there. Right? So you see the okay. It's like I no longer know how close I have to get to someone for them to see something. All right. You see it? I don't. All right, so the first thing we're going to do is just, again, Faraday's law, right? So what this guy is, it's called a variac, and that's just a nickname for variable AC. Right, so it goes into the 60 cycle per hertz, 60 hertz, 120 volt line voltage, and then it's got a variable resistor. All right, so the output can go anywhere from 0 volts to 120 volts, and it's going to stay at 60 hertz. Right? Okay. So I'm going to have a current that's going this way and then going that way. All right, so I'm going to have a B field that's going up, and then a B field that's going down. And it's going to smoothly change between them like a sine wave 60 times per second. Okay? So right through here, the middle of the solenoid, I've got a hefty changing B field. Out here, I've got a wimpy changing B field. So we pick the hefty one. And all this is a coil. They always wrap it up. I never know why they wrap it up. Okay. But the wires are going around in a circle. Okay, it's not a torus. Okay, so now I would have a changing flux through every coil of my coil. Sounds redundant, but it's the way you gotta say it. Okay, that's probably why they use turns. Every turn of the coil. So that ought to drive a current. So as I increase the voltage, I drive a current, right? Which means you can wirelessly power things. Like I said, this one's kind of wimpy, right? So I can't go too far away. But that's what I'm doing. Okay. The wireless chargers on your phone are doing that. Okay, now remember, anytime I got current going around, right, it becomes a little bar magnet. Right? This guy is a little bar magnet. What are their orientations?
Against each other?
Yeah, going to be against each other, right? Because as I try to push B field through in this direction, that's going to say no, and try and produce B field in the other direction. So I have this guy with the north pole up, that guy with the north pole down. They push apart, then it's going to switch and do the same thing with the south poles. Right? So if you feel it, I actually feel it. Got some vibration?
It's humming.
Yeah, about 60 or 120. I never figured out whether it's 60 or 120. I think once when it goes up and once when it goes down. So I think it's about 120 times a second.
Oh.
You guys okay? Come on, touch the low. Touch the high voltage, come on. Okay, what's going to happen if I, and like I said, this is wireless charging, right? What's going to happen if I turn the coil sideways?
Flip.
Yeah, nothing, right? Because the B field's doing this. So if I have the loop like that, none of it's going to go through. Okay, and so yeah, the current stops. Okay, so that's that part of it. This is a little more exciting. A bunch of loops, so I can have a bunch of current flow. Now you can feel the vibration better, or even hear it, and it sounds about 60 hertz, maybe 120. Oh, come on, back in the middle. Okay, so by the way, you can also feel the iron. It's starting to get warm after a lot of use, right? Because again, those little dipoles in the iron are flipping back and forth, right? So that's some motion that causes some heat. Aluminum is light, a lot lighter than copper. So with that, you can tell that it's doing Lenz's law, that it's creating north poles that are opposite a little more easily. Right? And again, feel it. You can feel the same frequency of the vibration. And then also notice the temperature.
Oh yeah. That's like magic. That just doesn't
Okay,
feel right.
how come it's getting hot? And it's not going to be burning hot.
Okay.
It'll be unpleasant hot. Okay.
It's not unpleasant hot.
Yes.
It will be.
I was like, right now it's not.
Neato.
Okay, what's making it hot?
Resistance.
That-
Ooh, cool.
There has to be a good comeback about it, because notice he did not say, I am hot. He said that, okay. Where does the energy lost in the resistor go? Heat. Okay, so I've got current flowing, right? And aluminum has a certain resistance. So, and I evidently have some fairly hefty current. Okay, how come it goes up only so high and then stops?
Just because your B field spreads out.
Yeah, so the higher I go, the less B field is going through it. So the smaller the changes, it goes up and down. Okay, so at some point I get to the place where the B field going through it is just right to produce a magnetic force that's equal to gravity, right? And so if I decrease the changing B field, then it has to get closer so that more lines go through. And if I increase it, I can take it further away, right? And so since it has an equilibrium position, it also does oscillations. It had gotten hot by then. Okay. So I imagine you can smell how hot it got. I imagine you can make it shoot fairly high. I was able to hit the ceiling fairly high with the last one. Okay, so again, I'm going to take this down. Okay, so again, no, it's that whole region of changing B field that gets encircled by an E field. So I have little circles all the way around, matching the symmetry, right? Since this guy is cylindrically symmetric, the E field will start circling at R equals 0 and do circles all the way out, just like it was B field from the wire, right? So what happens is going to be anywhere that I have that changing B field, I'm going to have little current loops going around. Right? Because I'm going to have the E field there. If I put metal there, I'm going to drive a current. Okay? When those things occur inside something solid, right, they're called eddy currents. vibration for a second. You usually don't want them, okay? But what it says is, now notice, here the B field's only going through this area. Right? As long as it stays at that area, it's fairly happy. I mean, it'll get a little hot, okay? But even if it's a constant B field, if I move it, right, that's taking the B field from one place to another, that's changing the flux through different parts of the thing, okay? So if I try and move it around, I'm going to feel a force that opposes that, right? Or the eddy currents are going to produce a force that's opposing that. Little current loops, a fringing field, it's like a magnet that feels a dipole magnet that feels a force in a non-uniform field, right? So kind of the next thing to feel is the eddy currents. Again, you can feel the vibration because basically it's a changing field, so it's trying to push away. But then try to move it side to side and feel what that's like. So you feel the inertia, right? Then you do it here. You feel the inertia. Do it slowly. Do it fast. Right? Change the rate of change, and feel the effect.
Is this where I get to ask about superconductors?
Huh?
Is this where I get to ask about superconductors?
A superconductor won't even let the field through it. Right? It will expel all of the things. It's really nice to have some quantum mechanics before you talk about it. Okay. What happens with a superconductor? The standard superconductor. There are different types. The electrons don't like to do the same thing. But by the same token, an electron that's spin up and an electron that's spin down is kind of like a stable form of a magnetic field. Right? So they like to stay at that orientation. And when they do that orientation, the combination of two particles has spin zero. Okay? Well, the basic idea of chemistry is that things with integer spin, you can all put them into the same state. And things with half integer spin, they all have to go into different states. Okay? So when I have that electron pair, then it's now an integer spin, and they can all start doing the same thing. Okay? That's not quite enough because probably they aren't doing anything at the beginning. So you need them to start moving along in the same direction. Okay? And the idea is that you have some vibrations that are traveling back and forth in the thing. And if it's at low temperature, the vibrations are very small and very close to a fundamental, so they're fairly big wavelength. And I know we haven't done that part yet. We do that third quarter. Okay. So literally, you get these electron pairs, and they surf the vibrational wave. Right? They just move with the vibration through the thing. And so traditional superconductivity is a quantum mechanical coupling of two pairs of a pair of electrons together with a vibration. Okay, and we were just doing that while you guys did it. But makes sense, you tried different speeds and stuff like that? Okay. How would I get rid of that effect? And unfortunately, I don't have anything that gets rid of that effect. So, but it's not hard to make. I just don't want to mess the other one up. How could you prevent currents?
By isolating them?
Yeah, in a way, by not letting them have a conducting path. Okay, so now if we look at this guy, again, wait, that gets hot too. Okay, so the flux is changing along here. Right, so the eddy currents would like to go through like this. right? But notice, I don't have a path in a circle around here, right? Because I go like, a fraction of a millimeter, and I hit that insulating layer. So this prevents the current from forming, which means it doesn't get nearly as hot as, say, that or that did, right? Because there's no I squared R loss. Okay. As a matter of fact, it's only up near the top when the current started going like this that I can start seeing things oscillate up and down. And it's the tip that gets warm, not the middle. Okay. So let's talk about another thing that does Faraday's law, because I don't think I talked about transformers, did I? No. So it's actually in a later chapter, but it makes sense to do it now. Okay, so here's another device. And I'll draw two models of it. The physics model and the practical model, okay? So here's the physics model. I'm going to do a solenoid here. It's a mini solenoid. And then I'm going to do a solenoid there. Okay. Does it make sense that, well, okay, so let's say the white one is solenoid number 1, right, called the primary. And the blue one is solenoid number 2, called the secondary. I'm only going to power the first one. Okay? And I'm going to send an AC current through it, right? That's why you don't do it right now, because you have homework problems that have alternating stuff, but they haven't talked about alternating stuff. But all I'm going to do is send a current through the thing that goes like some sine omega t. Okay? Makes sense? That's going to be just what we got over there. B field goes up, B field goes down. All right, so when I send an I1 in through here, I'm going to get a B field that just goes through there. Right? So notice that B field goes through every coil of the primary and every coil of the secondary. Right? Now the primary and the secondary don't have to have the same number, but I know it's the same B field through the same area for each coil of each. Right? So the basic idea is that the flux per coil is the same. And so the induced voltage, and they go back to using the script E, is the same for each. So I've got something where I say the voltage in the first one per coil is the voltage in the second one per coil. And so I get an induced EMF in the second one that is N2 over N1 times E1. So if N2 is bigger than N1, I get more voltage, right? And if N2 is smaller, I get less voltage, right? So if you get more voltage, they call it step up. If you get less, it's step down, right? And one of the neat things that AC current allows you to do is use the same power source, the utility, to power instruments that need different voltages. Right? That's why your computer that probably works on about 5 volts gets plugged into a wall outlet that has 120 volts. Right? Somewhere in there, there's a little transformer that takes it down to the correct voltage. Okay. Same thing for the chargers on your phone and everything else. Right, so the power bricks are basically little transformers. Right. Let's see what else I should say about that. Oh, okay. If you think about energy, right, you can't create energy, so the power has to be the same. Ideally, I mean, you're probably going to lose some power because there's probably some escaping flux. Okay, but ideally, you could say that the power that the primary gives is transferred to the secondary. Right. So that would also tell you. Remember, power is I times E, or I times V. Right. So the power ideally is the same. And so I1 epsilon 1 equals I2 epsilon 2, right? And so I2 is I1 times epsilon 1 over epsilon 2, and epsilon 1 over epsilon 2 is N1 over N2. Right? So what happens is when the voltage goes up, the current goes down, right, by the same ratio. Okay, that has some important applications. And so again, you go back to like 1900, and you've got a giant commercial war between George Westinghouse and Thomas Edison. Right? Both of them in New York City, both of them developing the electric age, right? And Thomas Edison was a good physicist, but he was also a very shrewd businessman. And what he did to sell electricity was he actually bought up a bunch of old steam plants that provided heat and ran cable cars and things like that from steam engines. They were neighborhood sized, and since he already was producing steam, it didn't cost him anything to divert a little bit to a turbine and to produce some electricity. But since he could only take the steam within the neighborhood before he condensed, right? He decided just to run the electrical wires together with the steam pipes. And so he had little neighborhood generating plants that produced electricity for his customers who were in the same neighborhood. Okay. And that was his model. And transmission didn't really matter because he wasn't going very far, so he just set the voltage and the current to what he thought people would use. And a GE appliance, right, because General Electric was Edison's company, right? Just basically was designed to have this much voltage and this much current. And his job was to get everyone doing the same thing, so that he could sell his appliances everywhere. Right? Westinghouse had Tesla as an employee, and Tesla was kind of a neat guy. And I have heard this story a number of times, and I'm not sure if it's true, but I'm going to tell it to you because why not lie? Okay. But the story I've heard a few times is that Tesla had to be sponsored to be able to immigrate to the country, right? He was a Transylvanian, right? The area of Dracula, together with about 4 other really famous physicists like Neumann, who started computers, and a few others. There were just like these 5 Transylvanians who were absolute geniuses and did fantastic work. Tesla was one of them, so evidently got sponsored, didn't know how to speak English. But to be sponsored, you not only had to have some family members there, but you had to have a job. Okay? So they got him a job at Westinghouse as a janitor. Okay? And Westinghouse in those days had what I think is kind of a neat way of doing things. We don't do that so much here, but have you guys ever walked through like a big university? Right? And you see outside of the professors' offices, they usually put up posters of what their research groups are doing. Okay. So it's slightly different with a company. Their interest isn't in telling you what they've done, it's in getting something done. Right? So the custom at Westinghouse was whenever they had a problem that they hadn't been able to solve in a reasonable amount of time, they would put a description of it on a poster beside their wall, outside their office. Okay. And then suddenly, strangely, people were coming to work in the morning and finding worked out solutions to their problems on the poster. Okay. And no one would admit doing it. Right? So as the story goes, Westinghouse actually hired detectives to set up a sting and to spy and see who was solving the problems without, people knowing that they were doing that. And so the detectives came in after a while and said, well, it's your janitor. Comes in the middle of the night, that's why you never see him, and he writes the solutions to your problems besides. And so Westinghouse immediately hired Tesla for a different job. And that's the story I've heard. But anyway, Tesla had a very different viewpoint from these neighborhood combined heat and power plants. He wanted to have centralized giant power plants, preferably that used renewable energy. Right? So his first power plant was Niagara Falls, right, where the falling water ran turbines and produced electricity. Niagara Falls is about 17 miles away from Buffalo, New York. So he also strung power lines, looked just like the ones today. He strung power lines for 17 miles to Buffalo, and with one power plant added distance, he powered the city of Buffalo. The trouble is, the resistance in 17 miles of copper plus all of the miles to get through the city of Buffalo wasn't negligible. Right? So the wires would get hot if you used DC. Right? And they would lose a lot of what they produced. So the idea was to go with AC because you can use a transformer. If you take the voltage really high, the current goes really low. Right? And so your I squared R loss is really low. Right? And so with that idea, you have high voltage transmission, right? Centralized power plants that are very efficient, and just lots of transmission to any place in the country that you want. And that's the model that made sense. And it's the one that the country adopted until Tesla won, right? Basically by demonstrating it with the Niagara plant. It wasn't sure who was going to win because Thomas Edison was famous and persuasive, and George Westinghouse was not. Okay. And Edison would do things like, of course, he also invented moving pictures, right? So he would take videos of people getting electrocuted, like convicted felons and stuff like that, and then put them as trailers of movies, take out ads in all the magazines and stuff like that, saying when they electrocute a person for killing someone, they use AC voltage. Do you want AC voltage in your house? Right, and so there was a lot of public outcry. My grandmother, right, who was I thought a really brave person, and she was like this little short red-haired German in Indian Territory, running a schoolhouse. Okay, but she was always scared of light sockets because she was sure that high voltage would electrocute you. Yeah, and it does hurt a bit. Okay, but it probably doesn't kill you, and it's not high voltage, right? But Tesla had to counter that, and Edison was just really good at marketing. Right? He marketed himself. He marketed all of his products. So what Westinghouse did was they sent Tesla out on the road, and he would sit inside this thing that looked like a jail cell for the person who's going to be electrocuted, but it was actually a Faraday cage, right? Because all the charge goes to the outside of the metal, right? And then he would hook up actual high voltage right on top of the jail cell, right? And you would see giant sparks all over the place because the electricity was arcing down to the cell and then onto ground. But because it was a Faraday cage and he was inside it, he was okay. So he would sit in a chair in the middle of this, giant sparks everywhere, reading a newspaper, and have motion pictures taken of that. and that was literally the emotional maturation that people were showing in trying to decide how to power America. And I've just always thought that was neat. Okay, but anyway, eventually common sense won, and it's Tesla. Even today, if we do a DC transmission, we first use a transformer to get to high voltage and low current. Then we rectify it, and then again, you still don't have any of the problems. But somewhere along the way, you had to have some AC. Okay, so